And then TJ is like, hey, I'm the That's the goal. That's what I'm trying.
Wait, you just have to take some.
Okay, let's get started. So this okay, this is chapter 16 section 16.6 on instantaneous center of zero velocity. So last class we talked about the relative velocity formula. Velocity of v is velocity of a plus omega cross rb with respect to a, where b with respect to a is the vector from a to b, like I've shown it here. Okay, so the way we think of instantaneous center is if a had a velocity equal to 0, so velocity of this point is 0, then this point a is called the instantaneous center of zero velocity. So throughout this course, we'll denote the instantaneous center of zero velocity as IC. So if A had zero speed, then it's called IC. If not, it's not an IC. Now there's something very simple about an IC, which is if you want to look at the velocity of any point, let's say B, then the velocity of point B is always going to be at right angles to the vector from A to B, like I've shown it there. So you know the direction, you just have to find the magnitude. The magnitude is simply the magnitude of omega times the magnitude of the vector from A to B, or RB with respect to A. So here are things about the IC. IC may be outside might be located outside AB, IC may change with time, or it might change as the object moves, and then IC may also be at infinity. So I can assure you that we always ask questions on IC in the exam. And locating an IC is just like drawing a free body diagram. If you know how to do it, then it's easy points. Okay, so pay attention to how I show you to find IC. It's not like FBD where you got to do some construction to find the IC. Let's draw the IC of simple objects, and then we'll do IC of more complicated mechanisms like the 4-bar linkage I showed you last class. Okay, so here is so some objects it's very easy and very obvious what the IC is. So here are examples of IC. So if you have a disk which is rolling then the question is, what is that point which has a speed equal to 0?
The point is touching the ground.
Right, so the point which touches the ground, this point is the IC because that point does not move, or the velocity is 0. So if you knew that, then you can actually find the velocity of any point on the wheel it's going to be 90 degrees, right? And so on. A pin link. A pin link has a pin joint which attaches the body to the ground like this, and clearly that point which is the pin joint does not move, so that's the IC. And then the final thing is a link which is pure translation which is you have a link and it's moving with uniform speed, it's sort of translating, then turns out that the IC is at infinity. Because there's no point whose velocity is 0. Everything is moving with uniform speed. If it was rotating and translating, that would have been a different story. But if it's purely translating, all points have same speed, then it has an IC at infinity. Okay, so those are the easier geometries whose IC is very easy to find because there is a point whose IC is equal to 0. Now, here are some examples you might see in the exam. So in each case, show graphically how to locate the instantaneous center of 0 velocity of link AB. Assume the geometry is known. Now, here's something to remember. Each link has its own IC. So this link, for example, has the IC over here, right? Because that point has 0 velocity. This link has its own IC, and that's what we are asked to find. Same for disk, same for that. That disk has an IC, this link has an IC. So it's specific to the IC. Each link has its own IC. Okay, and you're told to find the IC at this particular instance. Okay, so there is a specific way you do about it, and I've seen that in spite of telling how to do this slowly, 50% of the class does not get it right in the exam. But that's really easy points. Okay, so here's how you find the IC. So first is identify 2 points on the link whose direction of the velocity is known. Just 2 points, okay? Then draw vectors along the velocity directions of both points. Draw perpendiculars to the velocity vectors of both points, and finally the intersection of the perpendiculars of both the vectors gives the IC of the link. Okay, so I'm going to take this steps and show that how that translate to these 3 problems. Okay, let's just redraw the figures. So I'm going to start with A. Okay, step 1, find the velocity of identify 2 points whose velocity direction is known. Okay, clearly B is this point. It's going to move along the slope, so we know the direction of velocity. Okay, also we know that point A, since this point is fixed, let's call it O, A is going to have a velocity which is at right angles to that link OA. So I'm going to draw that first. So that's the direction of the blue dashed line is the velocity direction for B, and similar one is drawn for A. That has to be 90 degrees. That's always true, that the velocity of A is at right angles because the point O is pinned. Okay, the next step is to draw perpendiculars to the velocity vectors. So here is one of them. That's at 90 degrees to the dashed line or the velocity vector. And then the other one should pass through, it will actually be along the link OA because the velocity vector is 90 degrees. Okay, so this point here is the intersection of the two perpendiculars, and that is the IC.
And was this graphical representation good enough, or which one in there can't set up the same?
This is good enough. In fact, in the problem in the exam, what we'll ask you is, there will be a problem like this, and we'll tell you, draw it on that figure, do not even redraw it. So if, as long as you show those lines I showed you and you intersect them and show IC, you should get full points.
Is that just like half a problem, or is that one side of a problem?
Usually it's just part of a problem. Then you have to find the velocity, which is some of the problems I'll do today. But this typically, I like to give 4 points for drawing the IC, 2 points for figuring out the perpendiculars to one point, 2 points for figuring out the perpendicular points. So it's really easy points. And somehow people don't get it right. 50% of the class don't get it right, even after explaining it so slowly and doing it again and again. Okay, so let's do the same thing for the next problem. Okay, I'll do it on the same thing because I'm running out of space. Find the IC for B. Okay, again, find 2 points whose velocity direction is known. Clearly, A is one of those points because we know the velocity of A is at right angles to link OA. So dotted line. Okay, what's the other point? This C is shown, B is shown. Is C the point or B is the point? You have two options, C or B. B, I don't think I know anything about B, but I think I know something about C. Because C is the slot, the velocity at C has to be, well, I think the whole, sorry, my bad. Actually, C and B would have the same velocity, it will be along the link.
Wait, can you explain how the dashed line for A again?
Oh, so this is, I forgot to draw the right angle, but this is 90 degrees.
Okay.
The velocity of A is right angles because, let me backtrack and go back to my notes, which I made earlier. So why is the velocity of B always at right angles, 90 degrees? It's because if you try to do omega cross B with respect to A, let's do that vector cross, that cross product, okay? Move it down. Okay, so I'm trying to do this. This point has 0 speed, that's already in the formula. Omega is this way, and the vector from A to B is this way. So if I want to do omega cross B with respect to A, I need to do the vector points, omega vector points that way. The vector from A to B is this way. So I need to do omega cross B with respect to A, so I need to do this, this. Omega is this way, it comes out of the plane of the paper. A to B is this way. So this is my left vector, omega. This is my right vector. And then if I want to do the cross product, so it's like this. I need to do that cross this. So that term gives me the direction of velocity. So always 90 degrees. Provided A is at 0 speed. If A is not at 0 speed, then this is not true. Okay, so I explained to it, but I would recommend that you convince yourself that's right. That's 90 degrees.
So when you're doing this, one point has to pretty much be fixed.
It has to be, A has to be fixed, else B is not at right angles. Okay. Okay, so the link AB is constrained to move along the link AB. So dotted line is this way, and the next step is the last step is to draw the perpendicular. So one of them would stick out like that. That's the perpendicular to the velocity vector of A, and this is I see. Okay, let's do the same thing with C. We need to find the velocity. We need to find the IC of link AB for C. Again, 2 points whose velocity needs to be figured out. I would say B is one of them because B is going to slide along the plane. And then the other point is going to be A. Okay, what is the direction of velocity of A? So when you're finding if it's not along one of the inclines, then what you want to do is think which point has zero speed on the rigid body connected to A. So if it's a disk which is rolling, when a disk rolls, the point which is in contact with the ground has zero speed. So this point has zero speed. So now the velocity of point A is going to be at right angles to the vector from O to A, because that's exactly like the first scenario, or for that matter OA or this OA. So if I draw a line like this, then the dashed line is the direction of velocity of A. It is going to be at right angles to OA. So now draw perpendiculars to the velocity vectors at B and A. The perpendicular to this vector is going to be this. Yeah, so it's actually a mess, but that's where it is. So in the exam, we have a figure. We'll give you a figure. There'll be ample room around it. Just draw the IC on the figure. Do not redraw it. Just waste of time. Just try it on the figure. Okay, any questions on this? So please try to solve more problems. This is often missed concept. People don't understand this, but it's really simple, I think. Yeah, okay, it's just one figure. I drew that figure again just so that I won't clutter the first figure. Okay, determine the angular velocity of link AB. So we need to find this. At the instance shown, if block C is moving upwards at 12 inch per second. Okay, so there's only one figure, as I said. The second figure is only so that I can draw on that figure and not clutter the original figure. So we did a problem like this in the last class, right? We were asked to find velocity of, I think it was a similar concept, very similar, it's not exactly this problem. But the key is, if you know the velocity of C, you want to find a velocity of AB, then you find velocity of B using omega AB, which is unknown, and then link C with B using the relative velocity formula. And once you do that, you'll actually be able to solve for two things, actually. In this case, you'd solve for angular velocity of BC and angular velocity of AB. In other words, what I'm trying to say is that you do not need IC to solve this problem. I'm going to solve it using IC, but you do not need IC. You could use what we did last class to do it. So all these problems involving find angular velocity of this link or that link can be solved in two ways. One is what we did last class, and what I'm going to just show you right now, okay, using IC. And you may choose whichever you want for the exam. It's not like we want you to solve it with IC or relative velocity formula. Choose the one whichever you're most comfortable doing. Okay, so how do we do it with IC? So first of all, what we'll do is we'll always use the expression which I had written on some time back, that if you can find the IC, A is the IC, then velocity of point B is at right angles and given by omega times the length of the vector from A to B. Okay, so that's the formula we should be using again and again. So let me get started. So we know the velocity of C. We'll sort of try to find the IC of BC first. And once we know the IC of BC, we'll use the formula which I just shown you some time back. It is velocity of C and velocity of B can be found using the IC. So let's find, so the first step is find IC for link BC. Okay. So the same procedure, first identify 2 points on link BC whose velocity direction is known. In this case, I know the velocity direction of C. And another point which is clearly going to be B. The velocity of B is at right angles to the link AB because A is at 0 speed. So let me draw that. The next step is to draw the perpendiculars to link to the velocity vector. So that's one at 90 degrees to C, and then I need to draw the other one, which is going to be along link OAB, right? Because this angle is 90 degrees. So the point of intersection is the IC. No, it's IC for link BC. IC for link BC. What's the IC for link AB? What's the IC for link AB? Maybe answer the question, what is the IC for link AB? This is the IC for link BC. What's the IC for link AB? Just give me this. So IC for link AB is here, right? Because that's the link, that's the point which has 0 speed. But IC for link BC is this. So each link has its own IC. Okay, the second step is we're going to try to find the velocities of different points on BC using the IC. So in this case, velocity of C is omega BC times, and this is all scalars, I don't need to deal with vectors here. Omega BC is the angular velocity of length BC times R C with respect to IC. That basically means this length. Okay, so that's the property of finding the IC. If you know the velocity, if you know the IC, then that formula is always true. What always goes there is velocity of C is the velocity of the link with IC I found, which is BC, omega BC, times the vector from IC to C. Okay, but really the vector doesn't make, you don't have to show the vector because it's the magnitude, so we don't care too much about the direction. We also can write velocity of B equals omega BC times R B with respect to IC. Okay, so we are asked to find omega AB, but omega AB does not feature in any of those equations. Okay, in fact, VC is known, it's given. Omega BC is unknown. RCIC, which is this length, is basically a calculation in trigonometry. Okay, I'm going to show you how to find that. But if you know if this is a triangle, and if you know the sides of the triangle or some angles, you can actually find. Yes, so I'm going to assume you know it. We'll find it a little later. VB is unknown. Omega BC is unknown. Again, B to IC is a geometric calculation. Okay, so I just put down the knowns, unknowns, but still we do not know how to solve for omega AB because it does not feature in those equations. So now you can write another equation for. We try to write the equation for omega AB. This is using the IC. So this one used the IC for BC. Yeah. Yeah.
Can you explain again how you find the direction of velocity of B?
Direction of velocity of B is based on the fact that A is spin. When A is spin, it has zero speed. The velocity vector of B is always going to be at right angles to this 90 degrees, always, provided this is zero speed. Okay, you cannot do that, by the way, for C, because B is not moving at zero speed. You cannot draw it like that. Okay. Only when that is zero, this is 90. Okay, so I'm going to write another expression, this time for omega AB. The first two equations exploited IC for BC. I'm going to now exploit the fact that I know the IC for AB, it's just 0.8. So velocity of B is omega AB times R B with respect to A. And this actually uses the IC for AB. Okay, so omega VB is unknown, omega AB is unknown. I can't find the length of AB because that's given to me, it's 5 inches.
Question.
Yeah.
Why in equation 2, step 2, why are we using omega BC?
Because these equations are based on using the IC for BC. So I need to put omega BC here. But this equation here uses IC for AB, so it's omega AB which features out. I'm using this link, so everything associated with this link will show up in the first two equations. And for the third equation, I'm using AB, so only A and B will figure out. So the IC is basically this. It's almost like this link is, this point has zero speed, and this link is rotating about this point. Just ignore this for a second, but At this instant, it's going to rotate about this point, because this point has zero speed. And then you can think of this like a pin joint connected to this at 90 degrees. Pin joint. Okay, but that's true only at this instant. The IC will change as the object moves. That clear?
When you say RC, IC, you're talking about the distance from C to the point of intersection, so B is B.
That's CIC, that's BIC. Okay, so there are three equations, and if you look carefully, there are how many unknowns? There's BB, there's omega AB, and omega BC, three unknowns. Okay, and we have three equations. So we can solve for the three unknowns using the three equations. What is left is I need to figure out the lengths of links, this link, and this. Once I have those, I can easily solve for the three unknowns. So that part, solving for the links, is a trigonometric calculation I'll just do. Okay, so trig. So first of all, I know what RB with respect to A is. It's simply 5, right? Because that's given. Okay, I need to find this length and this length. I believe I know RBC. So let's draw that triangle again. This is 4. I need to find RCIC and RBIC. Okay, do I know anything else?
You know the obtuse angle.
I know the obtuse angle, so I know this angle. What's that going to be? So if this is 30, this is 30, this should be 60. So 60 plus 40 is 100. Okay, if I can find one more angle, then I should be able to solve for the
You
length.
know the internal input C is 30.
Yeah, you know this is 30 because those are I don't know, it's called a complement, supplement, not sure what it's called, but essentially this is 30, this is 60, this is 90, that should be 30 to complete the right angle. So that's 30. Okay, so let's so I'm going to use the sine rule because now I know. I can also find this. The sum of the angles is 180, so 135. So 55? No, 40, 45? Yeah, 45. So RCIC divided by sine of the angle opposite it, 105, equals RBIC divided by sine of the angle opposite it, so 45, and then RBC divided by sine of 45. No, sine, this should be 30. 45. And this is 4. Okay, so that can be used to solve for RBIC. The rules are up to here. And then once you do that, it's 3 questions, 3 unknowns. You can solve for the 3 unknowns. Okay, any questions? Okay, so here is a question for you. Let's do this together slowly. Okay, so as I said, I did this problem last class. Remember? We try to do the same problem using IC, and see sort of. I'll do some things, and I want you to finish the problem off. So let's first read the questions to determine the angular velocity of the rod and the velocity of point C at the instant shown. Okay, so we need to find the angular velocity. Let's assume it to be counterclockwise omega. Let's call it omega BA. And we need to find the velocity of C. So first step is, since there's only one link, we just have to find the IC for that link, and that's how we proceed. So 2 points whose velocity is known is B slides along the horizontal. So we know the direction of velocity of B. We also know the direction of velocity of A. So draw right angles to the velocity of B and that of A. So clearly this point is the IC. Okay. Second step is, let's try to first find the angular velocity of AB. So what do we know about, how can we relate omega AB to velocity? Well, velocity of A equals omega AB times R A with respect to IC. So I want you to try. I want you to solve for omega AB and pull the answer. Can you find omega AB from that equation? Yeah, I'm going to run out of time, so I'm going to stop at 10:46, 10:45. Cheers. Okay, so let's find the length of the vector from A to IC. What's this length? It's 3 because it's a 3, 4, 5 triangle, right? So this is 5. So the other side has to be 3 because that's a 3, 4, 5 triangle. So 3 is AC. So we have omega AB equals, should be 6 because the velocity is 6. So 2 radians per second. That's part A. Part B is we got to find the velocity of C. Now this is the best part. This is if you want to find the velocity of C, that's simply omega AB times the length of the vector from C to IC. You know omega AB, that's 2. You only have to find this length. So what's CIC? This length is 3, this length is 2.5, this length is unknown. Okay, how can we find? Well, do you know this angle? If you know this angle, you can use cosine rule. Yeah, so this is going to be 8 and 4/3, right? Let's call this theta. Tan theta is 4 divided by 3. Damn it. One more minute. (53 degrees). So you can find RCIC is going to be square root of 2.5 square plus 3 square minus 2. Let me just complete it. But basically, I was thinking of using the cosine rule, finding that, putting it here, finding the velocity of C. Okay, I'll see you on Monday.